Hello everyone, welcome to the video tutorial. In this video tutorial I will be solving a couple of questions from problem set number 3 using Stata. So the first question that I will solve today is computer exercise 1 from Wooldridge chapter number 4. So let's have a quick look at this question first. So here's the question. Question says that the following model can be used to study whether campaign expenditures affect election outcomes. So what we are trying to do here is, so we have two candidates here, candidate A and candidate B, and we will try to see if the expenditures by candidates A and B have any impact on the percentage of the vote received by candidate A, and the percentage of the vote received by candidate A is given by this variable vote A, and we have three explanatory variables here. The first one is expenditure by candidate A in logarithmic form. Similarly, we have expenditures by candidate B, again in logarithm. And the third variable that we have is party strength of candidate A. So it's a measure of party strength for candidate A, and it's basically given by the percentage of the most recent presidential vote that went to A's party before. Alright, so the first question that we have to answer is what is the interpretation of beta 1? So remember, this is an example of a level log model I talked about, I guess, in the first discussion section, the first lab session. So how do you interpret beta 1 here? Now look, whenever we have a level log model means the dependent variable here, it doesn't have any log term, so it's in level, but the dependent variable here, the independent variable here, or the explanatory variable, the variable on the right side, it's in log form, so it's a level log model. So whenever you have a level log model, to interpret the beta, what you need to do is you have to divide first this beta 1 by 100. So similarly, if you want to interpret this beta here, beta 2, because the associated variable here is also in logarithm, you need, and of course the dependent variable is in level, you have to divide this beta 2 as well by 100. But this beta 3, you don't have to multiply or divide this by 100 because the variable here, the explanatory variable here, is just in level, so it's not a log, it's not in log. So what we have to do is, as I said, you have to divide beta 1 by 100. So this beta 1 by 100, whatever you get, that value is a percentage point change in vote A when the expenditure by candidate A increases by 1%. That's how you interpret the beta 1. So suppose beta 1 equals say 6, you divide that by 100, you get 0.06. So 0.06 is a percentage point change in vote A when expenditure by candidate A, that is expand A, increases by 1%. Now remember that this vote A, this dependent variable, is in percentage, and that is why when we interpret this beta 1, we say that beta 1 divided by 100 is the percentage point change in vote A. So if this dependent variable was not in percentage point, rather it was in some other unit, maybe let's just say the dependent variable was in dollar, then our interpretation would also change accordingly. We would say that beta 1 divided by 100 is the change, say it's in dollar, is a dollar change in the dependent variable when expenditure A increases by 1%. So the change in the independent variable or the explanatory variable will be in percent. There is no doubt about that. But just be careful. The beta 1 divided by 100, the unit of that will depend on the unit of the dependent variable. So in this case, the dependent variable is in percentage, and therefore the beta, when you divide beta 1 by 100, that will also be in percentage. So again, the way to interpret this beta 1 is you divide this by 100, and then beta 1 by 100 is the percentage point change in vote A when expenditure by candidate A increases by 1%. I hope it's clear. Let's move on to the next question. The next question says, in terms of the parameters, state the null hypothesis that a 1% increase in A's expenditures is offset by a 1% increase in B's expenditures. So what it's basically saying is beta 1 is nullified by beta 2, or beta 2 is nullified by beta 1. In other words, beta 1 will have we will have a negative offsetting value from beta 2. So beta 2 will offset the magnitude of beta 1. So if beta 1 equals, say if beta 1 equals positive 5, beta 2 will be negative 5, or if beta 1 equals 1, beta 2 will be minus 1. So the question is, how can we write this null hypothesis? How to state this null hypothesis? So the way we can do this null hypothesis is you state the null hypothesis H naught equals beta 2 equals minus beta 1, or you could just write beta 1 equals minus beta 2, and if you rearrange that, you're gonna get beta 1 plus beta 2 equals 0. So that's the null hypothesis to answer this question. Later on we will see how we can test this null hypothesis. So far we have just only stated it, but we will show you how we can test this null hypothesis in Stata. Okay, let's move on to the next question now. Question 3, it says, estimate the given model, that is this model up here. Estimate the given model using the data in vote1.raw and report the results in usual form. Next part asks, do A's expenditures affect the outcome? What about B's expenditures? Can you use these results to test the hypothesis in part 2? So let's estimate the model first using the data in vote1.raw. I hope you have all downloaded this data file from iLearn. So let's go to Stata and open this data file called vote1.dta. Okay, so we have opened that. Now what we want to do is we want to regress vote A on log of expenditure A, log of expenditure B, and party strength A. So fortunately for us, we have all these variables already created here. So we have this log of expenditure A, log of expenditure B, and we also have the vote A. Vote A is here. So we don't have to generate any new variables, or we don't have to do any logarithmic transformations since they are already given in this data file. But I'm sure you already know how to generate a variable if required. For example, if you want to generate a logarithmic transformation, a variable through logarithmic transformation, just write gen, then the name of the new variable, let's just say LXP, then you just take the log of, say, expenditure by A, expend A. So you're transforming this expenditure of A into log and saving all the values into a new variable called LXPA. So that's gen, stands for generate. Okay, hope you already know that, but we don't have to generate any new variables here since we already have the generated variables here. So let's do the regression. So we write regress vote A, L expend A, then L expend B, and the last variable, what's the third one? Party strength, PRTY, STRA. Just be careful that we have all these A's in capital letters, so and Stata is case sensitive, so make sure you write the name of the variables exactly the way they are listed here in variables on the variables window. So hit enter. Now there you go, we get the results output here. So let's go back to the question. It says, do A's expenditures affect the outcome? What about B's expenditures? So let's have a look at the coefficient on log expenditure of expenditures by A. So the coefficient is positive 6.08, and the coefficient on expenditure by B, that is the value of beta 2, is here given by negative 6.615. So what we see here is that there is a positive impact of expenditures by candidate A on the percentage of vote received by candidate A, since this coefficient is positive. And also there is a negative impact, or there is a negative effect of the expenditures by B, candidate B, on the percentage of vote received by candidate A, because we have a negative coefficient here. Now, are these statistically significant? Let's look at the p-values for these. So the p-value for the first one is 0, which is definitely lower than 0.05, so it's statistically significant. The second one is also 0, so both beta 1 and beta 2, they're statistically significant here. So do A's expenditures affect the outcome? Of course it does. And what about B's expenditures? Yes, that also does affect the outcome. Can you use these results to test the hypothesis in part 2? Okay, here we go. Let's hold on a second here. Before we do the hypothesis testing, let's see if we can also interpret this number here, 6.08. How do you go about interpreting this number? It simply means that, remember, this is a level log model, so you have to be careful with the interpretation here. So this 6.08 basically means that if expenditure A increases, by 1%, then vote A, or the percentage of the vote received by candidate A, is going to increase by the 6.08 divided by 100, so you get 0.006. So let's just do that quick calculation here. Display 6.08 divided by 100, so 0.0608. So again, if expenditure by candidate A increases by 1%, then the percentage of the vote received by candidate A given by vote A will increase by 0.0608 percentage point. That's how you interpret this number. Now there is what you could also do is instead of dividing 6.08 by 100, you could just divide this by just divide it by 10, and then multiply this 0.06 and say similarly, instead of dividing so yeah, you just divide this by 10, and then instead of saying that we have a 1% increase in expenditure A, you just say a 10% increase in expenditure A would lead to 6.08 divided by 10, which is 0.6, I guess, 0.608 increase, a percentage point increase in the predicted share of the vote going to A. Anyway, let's just stick to dividing this by 100, and whatever you get is 0.0608. So that is the change in. So that's basically the increase in the percentage, or that's a percentage point increase in the vote received by candidate A when expenditure by A goes up by 1%. So let me just quickly write this down here if you want. So a 1% increase in spending by candidate A increases the predicted share of the vote going to A increases the predicted share of the vote going to A by about 0.0608 percentage points. Okay, that's how you interpret this number. Okay, cool. Now let's go and do the hypothesis testing. Remember, with the hypothesis that we wanted to test was this, that beta naught equals minus beta 2 equals minus beta 1, or beta 1 plus beta 2 equals 0 is the same thing. So let's go to Stata, and what we do here is just write test, then we write the name of the variable which is associated with the coefficient beta 1. So beta 1 is associated with basically L expand A. So write that with the name of this variable, expand A, and we write the name of the variable associated with the coefficient beta 2, because remember we are testing beta 1 plus beta 2. So beta 1 is associated, this beta 1 is associated with log expenditure A, and beta 2 is associated with log expenditure B. So log expenditure is given by L expand A, log expenditure B is given by L expand B. So let's write L expand B test. So okay, hit enter. Now we have the p-value here. So p-value is 0, so it's definitely less than 0.05, and we know if the p is too low, the null must go. So because the p is too low here, we reject the null hypothesis. That a 1% increase in A's expenditures is offset by a 1% increase in B's expenditures, so we reject this null hypothesis. Okay, time for the next question. The next question, it says estimate a model that directly gives the t-statistic for testing the hypothesis in part 2. So can we come up with a model now which will give us a t-statistic for testing the hypothesis in part 2? What do you conclude? Now, to do this, we have to do some rearrangement with the original model. First, we have to define a new parameter. So I have got them written down here for you guys. It will just quicker to go through what I've got here. Here we go. So this is our null hypothesis, beta 1 plus beta. So our null hypothesis was beta 1 plus beta 2 equals 0. So what we do here is we define a new parameter, theta 1, which is equal to this beta 1 plus beta 2. Then we rearrange this and express beta 1 in terms of theta 1 and beta 2. So we have a new expression for beta 1, and in the original equation we plug this. So we plug this expression for beta 1 into the original equation. So once we plug that in, so we replace beta 1 with theta 1 minus beta 2 here, and the rest of the terms remain the same. So we just replace beta 1. So let's have a look at the original equation if I have it anywhere. Well, it seems like I don't have it, but anyway, basically we had beta 1 here. We're replacing that with theta 1 minus beta 2 now. And remember, x1 is basically the expenditure by candidate A, x2 is the expenditures by candidate B, x3 is the party strength. So then just expand the terms. So you multiply theta 1 by log x1, beta 2 by log x1, do a bit of rearrangement here. And finally, what we do is we take beta 2 as a common factor, then we have log x2 minus log x1. So what's more important here is that we have this theta 1 present in our model now. So this theta 1, remember, is nothing but beta 1 plus beta 2, and this is what we want to test. We want to test if beta 1 plus beta 2, if this is equal to 0. In other words, if theta 1 is equal to 0. This is what we want to test. Remember the null hypothesis that we wanted to test? It was beta 1 plus beta 2 equals 0. So that's what we have here. We want to test this theta 1, which is nothing but beta 1 plus beta 2, and we want to test if this is equal to 0. So we have a newly stated model now, a new model now here, and this model can be directly used to test if beta 1 plus beta 2 equal to 0. So how would you do that? Let's go to Stata. So first thing that we have to do here, let's take a quick look at this model again. Let's go back there. So see, we have beta 2 times log x2 minus log x1. So you can think of this as a new variable, this difference between log x2 and log x1. So this is something we have to create first. We have x1, we have x3, that's a pretty strand, and we also have the expenditures by a, but we have to take a difference between log x2 minus between log x2 and log x1. Log x2 is the log of expenditures by b. Log x1 is log expenditures of log expenditures by candidate A. So we have to first create this variable in Stata before running this regression. So let's go back to Stata and use our usual command gen, which stands for generate. We want to generate a new variable called difflog, which is equal to log x2 minus log x1. So log x2 here in this variable list, it's called L expend b, and minus log x1. Log x1 is L expend a. Hit enter. We have the new variable called difflog right here. The next step is to run the regression on the new model. So we have the dependent variable vote a, then we write the independent variables. Remember, the first independent variable is log x1, which is basically L expend a. The second variable that we need is log x2 minus log x1, which we just generated, and we have called that difflog. So difflog. Then the third variable is unchanged from the original equation. I hope I have spelled them correctly. Hit enter. Now let's find out the coefficient that we're interested in, which is the coefficient on difflog, and we see it's a negative coefficient, and the p-value of that is 0. So it's definitely smaller than 0.05. So this coefficient on difflog is statistically significant. So what we say, we say that so we reject the null hypothesis that theta 1 is equal to 0. We reject the null hypothesis that theta 1 is equal to 0, which is the same as saying that we reject the null hypothesis that beta 1 is equal to negative beta 2. So just like the previous example, we failed to reject the null hypothesis. Okay. So I hope this question is clear to everyone, and with that note we will move on to chapter number 6, computer exercise 5. Go to page 18. Here we go. So we want to work on computer exercise number 5. Let's scroll down to find this. Here we go. So what we have is use the housing price data in hprice1.raw for this exercise. Estimate the model. So in this exercise we have to estimate this model where the dependent variable is a log of the price of the house, and the independent variable includes the log of the lot size of the house, then the log of the square feet of the house, and the log of the numbers. Sorry, there is no log here. The number of bedrooms in the house, and we have the error term. So let's go to Stata. Open our new file, data file hprice1. Well, I don't want to save. If you want to save, you can save, but I don't need to save. Okay, so let's do the regression first. And I'm sure you already are very familiar with this regression method. So just regress, then the dependent variable L price, and the independent variable L lot size, then L square feet, SQRFT. This is the second independent variable, and the third independent variable is BDRMS. So hit enter. So here we have the coefficients listed here. So let's just take a quick look. Well, it seems like both the lot size and the square feet of the house, both of these variables are statistically significant, and they have a positive impact, a positive effect on the price of the house, because the coefficients both for lot size and square feet are positive. And the number of bedrooms here, it's from the p-value, it seems like the number of bedrooms doesn't have a statistically significant effect on the price of the house. No, that's interesting. That's interesting. Okay, let's take a look at the second question. Now, the second question says, find the predicted value of log price when lot size equals 20,000, square feet equals 2,500, and bedrooms equals 4. Okay, so let's do that first. So what we're going to do here is just going to plug in the value of lot size 20,000 right here, and the square feet 2,500 right inside this parenthesis. Number of bedrooms equals 4 here, and we already know the value estimated. We have already estimated beta 1, beta 2, and beta 3 using Stata. So the beta 1 is 0.1, 0.16, beta 2 equals 0.700, and beta 3 0.03, and the last one is a constant, which is beta naught. So I have them here you go. So if you plug these numbers in here, you should get 5.99. So that's the predicted log price. This is what the question asked us to do in the first part. So find the predicted value of log price. So the predicted value of log price for these particular values of the explanatory variables is 5.99. Okay. Right. Okay. Let's go to the next part of the question. The next part of the question says, using the methods in section 6.4, find the predicted value of price at the same values of the explanatory variables. So far we have estimated the predicted value of log price. But what if we want to find out the predicted value of price from this model? From the same model, after the estimation that we have done, what if we want, or from this model, how do you go about finding the predicted value of price? Not log price, but price. So here you go. So suppose we have an estimated model like this. Estimated model. So we have the predicted value here on the left hand side, log y hat equals beta naught hat plus beta 1 hat times x1 plus beta 2 hat times log x2. Well, we could also have a log here, it doesn't really matter. We could also have a log before x1. So I deliberately included log here just to make a point that it doesn't matter if we have log before the independent variables or not. if we want to predict y. So to predict y from here, our first guess would be to simply exponentiate. That is, you just take exponents on both sides of this equation. Because if we take exponents on both sides of this equation, the left hand side will just become y. So if we take exponent on both sides, then this left hand side will just become y hat. This log will disappear, and on the right side we'll have exponent of beta naught hat plus beta 1 hat x1 plus beta 2 hat log x2. So this thing here, this highlighted part is nothing but equation 1. So this highlighted part is the same as log y hat. So we can just write exponent of log y hat. So that's probably our first guess, that probably this is how we should go about estimating the predicted value of y from the estimation that we have already done. But this is incorrect. This is not correct, because this usually leads to systematic underestimation of the expected value of y, that is y hat. It typically underestimates y hat. But it turns out that it requires a very little adjustment, which will help us get rid of this systematic underestimation. So that little adjustment leads to a model, an estimated model like this: y hat equals, so we have the same model as equation 2, that is y hat equals exponent of log y hat, but we have an extra term here which is alpha naught hat. So we multiply this exponent of log y hat by this factor alpha naught hat, and we claim that multiplying this exponent of log y hat by this factor will remove the underestimation that we had in equation number 2. Now the question is, how do you find the value of alpha naught hat? How do you estimate this? If you look at this equation 3, it just looks like an estimated model where alpha naught hat is the coefficient of the dependent variable exponent of log y hat, right? So what is the model that's being estimated here? If this is an estimated model, what is the actual model we're estimating? Well, it's no surprise, it's just the following model. The model which is being estimated in equation 3 is actually this equation 4. So y equals alpha naught exponent of log y hat plus u. This is the equation that's being estimated in equation number 3. So the original equation is equation number 4. So it basically means that one of the ways to estimate alpha naught is to regress y on exponent of log y hat. So our dependent variable would be y, and independent variable would be exponent of log y hat. So if we run a regression like this, then we can come up with an estimate of alpha naught hat, and then that's all we need, because as I said before, this is the factor that we need, which we need to multiply the exponent of log y hat with to remove the systematic underestimation of y hat. So quickly, just let's go over this one more time quickly. All that we're doing here is we have the model here that we estimated before, but this is in log y hat. We want to predict y hat. To do that, our first guess would be to exponentiate both sides, but exponentiating both sides would lead to underestimation, systematic underestimation. But if we take exponent on both sides, we'd be left with y hat equals exponent of log y hat. But since it gives us an underestimation of y hat, we need to make a little adjustment by multiplying it by alpha naught hat. So this alpha naught hat, this can be obtained by regressing y on the independent variable, which is exponent of log y hat. So I'm showing this to you guys to motivate the idea behind what we're going to do next to answer the second part of this question, that is using the methods in section 6.4, find the predicted value of price at the same values of the explanatory variables. So we want to find out y hat. We want to find out y hat when lot size equals 20,000, square feet equals 2,500, and bedrooms equals 4. So to do that, what we need to do first is we need to find out the value. We need to find out the value of log y hat when the explanatory variables take these values. Now we have already done that, haven't we? In the first part of this question, we have already found that log y hat is equal to 5.99. We did that just in the first part of this question. Let me just quickly show you that. So this is where we did that. We got 5.99. So we already know the value of log log y hat. But as I said before, we don't know alpha naught. We need to estimate that. To estimate that, we need to run this regression 4. So let's do that now. So let's go to Stata. So first thing that we need before we do this, so what we are trying to do here, we are trying to run a regression. We want to regress, what do we want to regress? We regress y on exponent of log y hat. So y in this case, in our example, is the price of the house. I think it's called price, yeah, price. And we want to regress that on what? Exponent of log y hat. But do we have the variable called log y hat yet? That is, do we have we already predicted the log y's? The answer is no. So if before we write this regression, we have to create this new variable, or we have to predict this log y hat, which is the log price hat in this case. So we want to predict that. So to predict, we write predict L price hat. So comma xp. I'm going to explain this now. So xp basically means linear prediction. So for a simple linear regression, for linear regression, you don't really need to write xp, but it's a good practice to write xp because it will be useful once we do probability logit analysis. So xp means do a linear, give us a linear prediction, and a linear prediction of price, of log of price. So what we are asking Stata to do is give us log y hat, and the values of log y hat will be saved under this variable L price hat. So we are creating a new variable L price hat, and it will contain all the predicted values of log y hat. And this command predict will only work after you have done this first regression. So after we have done this regression, so what we are doing here is we have done this regression, then we are trying to find out the predicted value of L price, which we call L price hat. Okay, so only after you have done this regression you can run this command predict. So let's hit enter. So let's see, we have a new variable called L price hat now here, and it's, if you look at the label of this, the label says linear prediction. Okay, and that's because we have done a linear prediction using xp, but as I said before, it doesn't matter if you don't write xp in this case. Okay, so we have got log y hat, which is L price hat, but we also need to convert into the exponent. So we create a new variable. So let's write generate gen m hat equals exponent of L price hat. Hit enter. So this m hat is nothing but this whole thing exponent of log y hat. So this exponent of log y hat is this m hat in this case. So now we are ready. We have our exponent of log y hat. We also have y. So y is nothing but price, and exponent of log y hat is the newly created variable m hat. So write regress price m hat. Now there's one thing I want to bring your attention to, which is that in this regression, notice that we have no constant. There is no constant term like beta naught or anything. There is a constant term in this regression, and therefore when you're running this regression you have to specify it, no constant. You write no constant here because we don't want any constant in this regression, and hit enter. Okay, cool. So what do we get for the value of alpha naught? So this alpha naught is a coefficient on m hat, and it's equal to 1.022. Okay, so we have the value of alpha naught. The next thing that you have to do, and I'll leave that to you guys. So next thing that you have to do is just plug the value of alpha naught here in equation 3. Plug the value of alpha naught here. Plug the value of log y hat here. We calculated that before, it's equal to 5.99. Take an exponent of that. So plug those two values, the values of alpha naught that we just got from Stata. It's equal to 1.02. 1.02, plug that in equation 3 and plug the value of log y hat, which is equal to 5.99, and see what you get. Okay, so that answers question number 2 from computer exercise 5. Let's move on to the next question now. The next question says, for explaining variation in price, decide whether you prefer the model from part 1 or the model price equals beta naught plus beta 1 lot size plus beta 2 square feet plus beta 3 bedrooms plus u. So what's the difference between this and the first model and the second model? The difference is that we had our dependent variable, we had that in logarithmic form, but here we have in level form, and also we had the lot size in log, square feet in log, but in the new model we have got rid of these logs here in the dependent from the independent variables. So question is, how do these two models compare? Now you might want to compare these two models using r squared, but the problem is you can't really use r squared here. So you could just run this regression, look at the r squared, and then run this regression and get the r squared and compare these two, but that doesn't really work. That doesn't work because in both in these equations the dependent variables are different. The dependent variable here is in log, but the dependent variable here is in level. So whenever the functional form of the dependent variables are different, you can't really use r squares to compare the models. You can't really use r squared to judge which model is better than the other. So we have to do a bit of trick here. What we're gonna do here is remember that what is r square? R square is a correlation between the dependent variable and the predicted variable, right? So it's the correlation between y and y hat, or it's a correlation between. So let's just go back to what I wrote before here. So for this model, r squared would be nothing but the correlation between log y and log y hat. That's the interpretation of r squared. That's one of the interpretations of r squared. So that's how, because this is a very simple way of defining r squared or estimating r squared, we can use this idea in answering this question. So the first thing that we'll do is we run this regression. So let's go to Stata, regress, price, lot size, square feet, bedrooms, enter. Run this regression. Now let's have a look at r squared. It's 0.6724, but we can't really use this r squared to compare this model with the previous one. So even if we do, let's just go back. Let's go up where we had the original model. This is the original model. R squared is 0.64, but here in this model, in this level model, r squared is 0.67. So it appears that the r squared is higher for the level model, and that might tempt you to think that the model in level is probably better than the one that we had before, which was in log, but that is not true. As I already said, you can't really use r squared to compare models when the dependent variables have different functional forms. So this result is gonna be useful. This is 0.6724, so the r squared is 67.24%. But if you calculate the correlation between price, so if you run this code core between price and m hat, so that is let me see. Okay, let's just leave it there. So just correlation between price and m hat, you'd see that the correlation is equal to 0.8589. But as I said before, r squared is just the square of the correlation between the dependent variable price and the predicted variable m hat. So it's just 0.8589 square. So this is not gonna work, of course. So what you can do is just write display this. So here we go. Here we have the r squared. Then first we calculate the correlation between price and the predicted value of price. Remember m hat. Okay, let's go back how we define m hat. M hat, this was the exponent of the log price hat. So oops, let me quickly go here. So m hat was this. M hat was this. And what we have effectively done here is, what we have tried to do here is we have tried to compare this model 1 with model 4, and oh, oops, let's step back. No, what we have tried to do here is we have tried to compare the model in level, which we estimated in Stata. Let's go back to Stata again quickly. So these r squared with the one when we have logs. So for the log model, the r squared is equal to 0.7377. So definitely for the log model, the r squared seems to be higher than the r squared that you get from the level model. Okay, so therefore the log model is better than the level model here. Okay, let's move to the next question then. That's computer exercise C9. That's from chapter 6 again. So C9, here we go. It says the data set nbasl.raw contains salary information, career statistics for 269 players in the National Basketball Association (NBA). So estimated model relating points per game to years in the league, which is given by the variable called xpar. Then age, years played in college, include a quadratic term in xpar, which is experience. The other variables should appear in level form. Report the results in the usual way. So let's open the file NBA. Okay, so we are asked to run a regression of the form regress points experience, a quadratic form of the experience as mentioned in the question. So xpar square. It's already given here, the square of experience. Very good. Age of the player, and what else? We need age of the players, and okay, and college, and years played in college. Call, hit enter. There we go. We have the coefficients. Very simple. So why do we have a squared experience here? Why do we have this squared term? The squared terms are included to capture decreasing or increasing marginal effects. Okay, that's why we include these squared terms here. So let's have a look at the coefficients. It seems like experience X bar is years in the league. How many years a player has played in the league? It seems like it has a positive effect on the points per game. And experience squared, it has a negative value. And age seems like it has a negative impact on the points earned. Okay, so let's go to the next question now. Oh, before we go to the next question, notice that we have a positive coefficient for experience, but a negative coefficient for experience square. So whenever we have a positive value for x and a negative value for x squared, it basically means that we have a U-shaped curve. Okay, it basically means we have a U-shaped curve. So for lower values of x, beta 1's positivity will prevail, and for higher values of x, beta 2's negativity will prevail, and therefore the curve will be U-shaped. Okay, so let's go to the next question now. Next question says, holding college years and age fixed, at what value of experience does the next year of experience actually reduce point per game? Does this make sense? So it's basically asking us to find the turnaround point of x, or turnaround point of experience. The formula for turnaround point of experience is, so if the model is given by this, y equals beta naught plus beta 1 plus beta 2 x squared plus u, then the turning point of x is xt equals beta 1 hat, negative beta 1 hat divided by 2 beta 2 hat. So from the previous regression, from the regression that we have just done, beta 1 hat is equal to 2.36, beta 2 hat is negative 0.077. So plug these in this formula, and you should find a value equals 15.35. So that basically means the increase from 15 to 16 years of experience would actually reduce salary. Now this is a very high level of experience, and we can essentially ignore this prediction. In fact, only 2 players in our sample of 269 they have more than 15 years of experience. You can check that using the summary command that I showed you previously. Okay, I'm going to skip question 3. I will leave that to you guys. Seems like question 4 is also the same as question 2. I'll leave that to you as well. So question 5 asks you to run a regression log wage and points. You can do that using the regress command. Very simple. Then question 6 asks you to test whether age and college years spent in the college are jointly significant in the regression from part 5. All that you have to do is just, after you have regressed this model as stated in 5, you just run a new code for 6 to test whether age and college call are jointly significant. For that, you just have to write test age call. After you do this test, you should find the p-value, look at the p-value of the f statistic and see if that is lower or greater than 0.05. If it's smaller than 0.05, you reject. If it's greater than 0.05, you fail to reject. So before you write this command test age call, you have to do the regression in 5. So after you do the regression, then to answer question 6, you just write this command test and these two variables age and call, because we want to check whether age and call are jointly significant in the regression from part 5. So I think that's all for today. I hope I have answered all the questions, and if you have any further questions, please feel free to email me. Okay, see you guys in the class.